So I'm very, very happy to be here today. So thank you very much for the invitation. It's very good. I mean, we fly all the planet, and then sometimes we miss maybe opportunities in the Montreal metropolitan area that is extremely rich in terms of research possibility to collaborate. So I try to be careful, okay? I try to be careful now using the words that they could go through electronics, a little bit of chemistry, biology, biomedical. I will try to be as clear as I can, okay? But I belong to a Department of Engineering Physics, so maybe for me, concepts in bio are less familiar than for you, so maybe you will have input to rectify some of the contents. Let's see. So, Polytechnique Montreal, as I was saying, Engineering Physics Department. Let's look at the title 1 second of what I would like to share with you today. So, there is a towards green, that at this point I would say greener, not green. Very difficult to measure what is green at this point, to quantify. The melanin case, so we will focus on a certain class of materials that have the potential to bring us towards a little bit greener electronics without dreaming about a rapid and easy revolution in the field of electronics. So if you see the words electronics here, it means already that maybe I'm not totally in the bio field, but there is a limbo, I guess, between the environmental issue and earth issue, and I think it's here the pertinence of my seminar here. Maybe I'm not totally right, we will see. So, first of all, impact of our research in the sense where we are. Let's imagine that what we are investigating really all the promise of what we have in mind. Which area are we dealing with? The area of bioelectronics, so an area that is at the interface between biology, you are the expert, where so the ionic movement is predominant, and the area of electronics, where electrons and holes are the predominant charge carriers. So we are at this interface. So good contribution, of course, you have in your program very good researchers, some reference researchers at the global level might be, for instance, George Malyaras now in Cambridge, or Magnus Berggren in Sweden, a number of good scientists, Jonathan Rivney in Northwestern. In this sense, so the use of, for instance, biocompatible materials, it's important in the sense, I mean, for the surface modification, chemical interaction, but so the use of biomaterials for people in bioelectronics, I would say, is more on the biocompatibility side. For me, for my research group, the interest in biomaterials, and we could already define a little bit what I have in mind when I use this word, is more for environmental concern, let's be honest. So here we have a book that is just, I mean, a few weeks, it is on the market since a few weeks, so Green Materials for Electronics. The key author, I would say, is Dr. Mihai Irimiavladu, now he's in Austria. And so for me, as for, I would say, other scientists in the field, we look at biomaterials as one of the possibilities to make electronics a little bit more environmentally benign. Now, I don't want to be naive either. The field of green electronics is a very challenging field in the sense that I'm totally aware at this point we're dealing with Samsung, we're dealing with Apple. We don't. It's kind of challenging somehow. But it's also true that we have to start somewhere, since both the microfabrication chemicals are not always the most environmentally friendly, the less hazardous, the most abundant. And more than this, a concern for me, I will come back to this slide in a few seconds, is the accumulation of electrical and electronic waste on the planet. So the fact that I think we missed an important point in the supply chain, in the electronic supply chain, that is, okay, and what's going on at the end of life of my electronic device? So what we do with the organic fraction and the inorganic fraction, metal containing precious metal most of the time of my device. So one concept for me, it was, so let's go through biosourced materials, most of the time, so carbon-based materials, as one of the way, beside reusing the devices and beside recycling the device, to kind of a path toward a more environmentally benign electronics. So at least it's very important for me. So I don't want to say the way I propose, the way my research group proposed, the way my collaborator proposes is the only one. By far, so we have the reuse of electronic devices, recycling of electronic devices, and then the exploration of novel materials and processes that are more environmentally friendly. So in this context, my study of organic, so carbon-based, biosourced materials. Of course, these materials have to be somehow electroactive, so both they have to feature charge transfer or charge carrier transport properties to be eligible, I mean, for them to make sense to be investigated in the context of electronics. So one concern was really the accumulation of electrical and electronic waste. The second concern is what we could call the embodied energy in an electronic device. So how much energy do we spend to manufacture, not to operate, to manufacture? This is an amount of energy that is higher with respect to the energy or the power that we use during the operation of the devices. So recently we really assisted at a conversion somehow. So it's higher, the energy that we use to manufacture than the energy that we use to operate a device. And this is a concern. So we should try to go for processing condition that limit, if you want, this embodied energy. And for instance, in this sense, solution-based techniques, somehow something like printing, maybe you are familiar with printing. I don't know if you're more familiar with 3D printing or with the printing of thin films for optoelectronic devices, but I mean, being a processing approach that uses ambient condition is expected to be, let me use the word expected to be, at least in principle, more environmentally benign. What is surprising, and here I don't particularly like marketing, but what is surprising is the lack of knowledge in this field. So how I quantify the embodied energy and how I can limit this embodied energy, or how do I evaluate the life cycle of a device. The lack of knowledge is impressive. We are organizing at Polytechnique Montreal, forgive the marketing maybe tone of this information, a workshop funded by NSERC on sustainable electronics on the 3rd and the 4th of December. I'm going to send a little bit more information on this. So we will have 2 days where even, senior engineers from Intel were super happy to jump in and to give their contribution after a life in the Silicon Valley, for instance, to see what are the environmental concern of the electronics we use nowadays, especially considering the lifetime of a mobile device, okay? We have an iPhone for 1-2 years, and so what? What do we do after this? A lot of environmental, and not just environmental implications. Anyway, just to make things, just to show you a little bit more now, again, the context, I see, look how delicate is what I called before, I used the metaphor limbo somehow. So you can find in journals, in material chemistry, material science journal, title like Biodegradable Electronics, cornerstone for sustainable electronics and transient application. I would like to talk to you because this is very important for biomedical, bioengineering people. Biomedical, biology, bioengineering, I'm a bit confused at this point, but. And then we also see, for instance, the search for biosource materials. So, for instance, in the case of this title from Chemical Review, wood derived materials for green electronics, green, so environmental, biological devices, and here we go on your word, and energy applications. Is it a mess? Or it's really difficult to be clearer than this, even just in the title of good articles in good journal. So I give you a few seconds of my experience. So here we have a few keywords. Biodegradable, sustainable, transient. Do you know that transient electronics exist? Anybody is aware of the existence of a research field that is transient electronics, apart from, I guess, Noemi, not even on the discussion. But so in electronics that is really supposed, where the devices are really supposed to dissolve at the end of the service life of the device. And it's really the scale of minutes and really the scale of hours. So I can ingest a biomedical device that dissolves, for instance, because of the pH of my stomach. And this is something, for instance, and so you use electrodes that can be magnesium-based or iron-based. A bit different is the concept of biodegradability that comes with the concept of compostability in environmentally benign device. So I think there is a certain overlap, but we should try to be as clear as we can, even if the field is really forming now, so it's not possible to to establish clean categories and everything is absolutely defined. But what is really a little bit more confusing, but again, it gets closer to the reality actually, is even the fact that there is a certain continuity between, so the environmental sustainability, Earth, if you want, and energy. And why energy? Because sometimes, you can store electrochemical energy in materials that are not always, lithium iron phosphate, but even carbon-based material can store energy. They can have redox functions such that you can store charge, so you can store energy. For instance, quinone-based molecules. And this is the case of what I'm going to discuss today. So this bio-sourced material can be important for their biocompatibility. This is more maybe your field, for an environmentally benign electronics, and also maybe indirectly, if you think that you have to power your electronics, or that in any case you have mobile devices, and then you want so this autonomous device equipped with powering elements, and the more these powering elements are environmentally friendly, the best it is, of course, for the environment, even in the field of energy. So this carbon-based material, they can take us very far. Now, I will not focus today on results on biodegradability and compostability. Maybe we had a little misunderstanding, Sebastian, on this. I will talk about other things, even if these results have been collected and now are under review, actually. So, again, just to make things clear, and then we really enter in the core of the original results I want to present. So when we use the word biodegradability, there are really standards at the international level that are recognized. And so, for instance, when I want to define a plastic compostable, I know what are the steps, the exam, if you want, that I have to pass, the experimental conditions that have to be respected. This is just for plastic, not for plastic electronics. This is for plastic that we use in our bags somehow. But if in the field of plastic electronics, that is somehow my field, there are no criteria to define the compostability of a plastic electronic materials, even less available are criteria to establish the compostability of an electronic device. And I can tell you that there is a lot of interest at the international level, at the industrial level, but no international standards are available. So there is room to work, I think, at the university, especially, in collaboration with National Research Council. Their mission is really this one also, to helping establish regulations. With the National Research Council, since now 1-2 years, microbiologists there, we have a very interesting, in my opinion, collaboration really in the field of how to compost electronic materials and devices, of course, carbon-based. I think at this point it's clear then you are interested in the end of life of the device for environmental issues or for biomedical. Let's not talk now about oil spills or military application, military interest. That is anyway absolutely, absolutely strong, I know for sure. So, let's say something now. If we discuss about natural materials in the field of optoelectronic devices or energy storage devices, let's not think that this is the first trial. Can I have a little bit of attention? I focus a lot, and so I need some silence in the room. So if we make an effort in terms of exploring natural materials, we're not the first one, of course, in the history of material chemistry, material science, to investigate natural materials. So a few years ago, indigo-based, and indigo is really the dye that colors our genes, have been used as semiconductor in organic field effect transistors. They work pretty well. I mean, the mobility, so the drift speed per unit of electric field of this, in this device is like in amorphous silicon. So it's relatively good somehow. They are stable in ambient conditions, so of course there is an interest. I cannot even mention the number of studies available in the field of dye-sensitized solar cells, so a number of dyes extracted from natural sources have been used to improve the matching between the solar spectrum and the absorption of semiconductors like titanium dioxide or tungsten oxide. So all kind of chlorophylls, for instance, have been investigated, I would say, during the 80s, beginning of the 90s, in particular in the group of Michael Gretzel at the Ecole Polytechnique de Lausanne. For me, we will try to focus now on this specific class of pigments that are melanins. And even more, I mean, in the subclass of melanin that is eumelanin. So eumelanin is the brown-black category belonging to the melanin pigment family. You also have pheomelanin, other type of melanins, so among them pheomelanin. It's a red-yellow pigment, and what it's interesting, and it's a subject of research in itself, is in our brain we have what we call neuromelanin that is actually a core shell structure resulting from the combination of eumelanin and pheomelanin. This is in what we call substantia nigra of our brain, so it's very interesting to know why a colored material is present in a non-illuminated region of our brain. The hypothesis up to now that scientists propose are that melanin is there to control the flux of copper, iron ions, among others, so you can use it as a reservoir and as a sink of, in principle, oxidative ions. But this is a topic of research. I really would like to study this more, didn't find yet good collaborators in this, for this problem. It's for sure not in my expertise. Okay, now, if we talk more in chemical terms, melanin results from the combination of these two building blocks. These are called indoles. Here there is a benzene ring, here there is a pyrrole ring, condensed, and so this is an indole. And you can have building blocks where you have the simple 5,6-dihydroxindole, or where this 5,6-dihydroxindole is functionalized by a carboxylic group. For sure, this carboxylic group confers proton transport activity to the biomaterial. What is interesting, and for sure it's important for the energy storage, is the fact that we have a redox active group in our building blocks, and so this is the hydroquinone form of the building block, this is the intermediate redox form, and the quinone is the oxidized redox form. It's interesting that every time that I have an oxidation, so the release of an electron, I also release a proton. So this is a kind of a proton-assisted electron transfer, and this is very important for what we're gonna tell after. So it always happens, at least maybe even after conference, people come to see me, how did you get this idea of this melanin, where it comes from? So if you look at, now the field is booming, and I'm telling to myself it's time to leave, honestly speaking. So a question of 1-2 years, and I think we have to open other venues, and now, I mean, I think younger researchers can keep going. But if I entered the field, it's because I read about this melanin in completely different source of, different journals, if you want. Anyway, it is electrically conductive in an hydrated form. It's stable in air and in water. It is biocompatible. There are somehow studies that are not totally conclusive, but anyway, in the group of Bob Langer, so at MIT, they studied a little bit the biocompatibility of melanin, and it's apparently decent. I don't want to use other adjectives. For an engineering physics department, or the physical chemist that I am, for me it was extremely important to know the good UV visible absorption properties of the material, the fact that you can chelate metals, so you can kind of grab metals. You can really, like a crab, at a certain point, you donate electrons that come from these pi clouds to electron-deficient metal center, but also the free radical quenching properties. Here, I'm just entering the field in this last year. It's extremely interesting, if you ask me. It's extremely interesting, but we are relatively new. We just have one publication in this, in this field. And of course, cosmetic industries know about it. So, why I show you now this slide? First of all, when you talk about plastic electronics, and more or less is the same synonym of organic electronics, is that you always think about these alternance of double and single bond. So these alternance of double and single bond ensure, if you want, an abundance and a certain type of path available for electrons or for holes to move like if you were in a semiconductor. So it is kind of important. I mean, it's not a chemistry department, but I think you have to like molecules if you deal with bio. And so the aspect that for me it's very important, and where a lot of science can be generated, is the fact that we have these alternance of double and single bond. So this delocalization of the electrons give you the chance to have intermolecular charge transfer. So from one chain, if you want, to the other, from one molecular orbital to the other. This other type of functionality here, more I would say carbon-centered, give you the chance to have intramolecular charge transfer. So the intramolecular charge transfer, the Kinnon group will permit us to store electrochemical energy. The conjugation, so the alternance of double and single bond, will permit us to dream about semiconductivity in the melanin. But maybe this is not priority for you. In terms of self-assembly, in terms of supramolecular aggregation, how, once the covalent bonds are established, the material form, so we observe a typical pi-pi stacking. Here you are absolutely the expert, so with distances that are in the 3.5 angstrom range, but we also have, apart from the pi-pi stacking, hydrogen bonding interaction for the monomer, for the when the building block, carboxylated building block, is involved in the included in the material. We'll not spend too much time, but we spent a lot of time in the understanding of how the material, in observing by atomic force microscopy, what is the morphology, what is the aggregation of films of melanin spin-coated on substrate, typically silicon dioxide. We spent a lot of time. We are in an engineering physics department. We fabricate devices. We go from the material to the microfabrication, to the fabrication of the device, and to the optoelectronic characterization. So for us, if we do not control, if you want, the supramolecular arrangement, it doesn't make any sense to study charge transfer or charge transport properties in this material. So it's very important that our shelf or the literature, I mean, we shed light on how molecules get together and how atomic molecular orbitals overlap. Now, from the physics point of view, it's interesting to know that we had a few seminal papers at the end of the 60s or beginning of the 70s on melanin being the first amorphous, I would add, organic semiconductor. There is something that maybe it sounds not so interesting for young students, but I think it's important to know that in 1977, a chemical communication paper proposed the existence of conducting polymers. So iodine chemically doping polyacetylene. It's the first report that maybe organic materials are not there just to insulate, but they can also conduct charge carriers. This led to the Nobel Prize in Chemistry in 2000 for the discovery of conducting polymers. So the first report is 77. Here we are in 74, and it's not the first science paper produced by this group. So somehow we could discuss on what has been the first report on the electrical response of organic materials. Anyway, this is to say that for decades, melanin intrigued really material scientists, physicists, to understand, is it really a conducting material? And if it's an electrically conducting material, is it a semiconductor? And if it's a semiconductor, is it a conventional, in terms of band semiconductor, or it's an amorphous semiconductor? Decades of study, this paradigm was kind of well accepted till when more recently another type of mechanism has been proposed where melanin would be, I don't enter into the details at this point, would be a mixed ionic and electronic conductor. So the group of Paul Meredith proposing that there is what we call in chemistry a comproportionation reaction between the reduced form of the building block, hydroquinone, oxidized form of the building block, quinone. In a wet environment, I have protons and I have intrinsic spin radicals, electronic charge carriers, ionic charge carriers, so maybe something has to change in the melanin field, in the melanin physics. That is, maybe it's not only the only possibility to explain the electrical response is not the amorphous semiconductor one, but maybe it's what we could call now in a fashion way an iontronic type of behavior, a mixed transport, ionic, electronic. This is, of course, good for the bioelectronics application. We decided to give our contribution because you have different schools proposing different models, and we decide also, and maybe Sebastian, you followed this part of the talk when we met in Toronto, we decided to make a step back. So the field is too complicated. Let's try to simplify. Let's try to study charge transfer before studying charge transport. That is actually a sequence of charge transfer steps. So we went to run electrochemical experiment, and here you might be familiar. So these are cyclic voltammetry experiment. I have the current on the y-axis. I have on the x-axis an electrochemical potential with respect to a certain reference electrode. And what we observed is kind of a box-shaped voltammogram. So usually, now the board here is a bit small, but usually, when you run this type of experiment, you expect also peaks in your voltammogram, peaks that results from diffusion mass limited processes. So the charge transfer processes happen, and then its advancement is somehow limited by the presence of mass transport effects. Here we have a box-shaped voltammogram. So what does it mean? That we don't have charge transfer? Not really, because if we we know that we have Kenon groups in our molecule. Most probably, this is the baseline of our current collector. So carbon paper, micrometric fiber of carbon are the carbon paper. So most probably what we are looking at here, and is something that is very common with natural materials that are chemically disordered and physically disordered, is a convolution of redox sites that give me a box-shaped behavior even if redox processes are there. So we call this type of behavior, and maybe in the biofield you know what I mean, pseudo-capacitance. So I don't store charge simply because of electrostatic effect, but I store charge because of redox processes beside, electrostatic processes. So melanin behave as a pseudo-capacitive behavior, and here with the increase of the sweeping rate, I prove the capacitive behavior. So with the linear increase of the current with respect to the sweeping rate, we prove the capacitive behavior of our material. That if we go into the insight, into the interpretation of the results, is actually, as I was saying, a pseudo-capacitive behavior. Faradic processes take place beside electrostatic interactions, okay? So this, I think, was a good result, even because we could somehow design and develop a certain technology. So, of course, if we know that we can store charge with a biosourced material that is biocompatible, and we just solution process this material in ambient condition, this is an interesting result in itself. And so we fabricate our electrochemical energy storage device. Actually, what we developed, these are the, maybe here a bit of context, but these are the typical characterization of the supercapacitor, in our case, melanin-based device. After this, we also developed microsuper capacitor. I tell you that microfabrication is really an important component of our activity, and we fabricate this device on flexible substrate. This, the first report was on polyethylene, but now we try to do something different. So polyethylene polyimide, it works, but we try to go for biodegradable plastic like PCL or PLA, polylactic acid or polycaprolactam plastic, type of plastic, because of their biodegradability, of course. Here, if you allow me other 5 seconds of physics, I think it's very nice to see, even when you want to develop a technology, you really care about the applications, it's kind of very interesting, in my opinion, to associate the convolution of the redox active sites that give, at the end of the day, a box-shaped behavior to the featureless absorption spectrum of melanin. So this is a typical absorption spectrum. Here you have the absorbance, here you have the wavelength, you go from the near infrared to the ultraviolet. It's really a broadband spectrum. One of the models that people invoked to explain this featureless spectrum has been the presence, spectrum like a convolution of the absorption of different chromophores that at the end of the day results in this featureless spectrum. So kind of a chemical disorder model. And at the end of the day, I think we could really establish a parallel between the featureless voltammogram, the featureless optical spectrum, to say, hey, these are natural materials. They are not synthesized in the lab. So their purity, the different polymerization sites for the 2 building blocks, we cannot pretend physical order, so even in the supramolecular organization. So it's kind of intuitive that you have this kind of convolution behavior when you go to measure, the physical properties. And another element, apart from the development of a flexible microsuper capacitor, there is another element that especially here I would like to raise. So what you see in the scanning electron microscopy image are carbon fibers at the micrometric scale, and then a little bit of here and there of white clear spots. Actually, to image melanin on carbon current collectors, we had somehow to stain Even in electron microscopy, you can stain. And a few studies we did even here at McGill. Then I think we kept going on campus, but okay, there is a wonderful facility here too. So, point is that we had to stain because you want to reveal carbon on carbon. Okay? And what we used has been actually an uranyl staining approach. So we said that melanin has good ion binding properties. This salt is no exception. So we were able to stain with a heavy atom our melanin. We were able to reveal where it is not, our melanin on the carbon current collector. So for me, there are implications that, I mean, it was also a way to explain to the student the continuity between, I mean, you work in science, there is no clear frontier between one discipline, one interest, and the other. So we should kind of develop this intuition in the sense, if uranyl stain well my melanin that I want to image for my specific electrochemical energy storage device, there are good chances that melanin also block uranyl salt in my skin. Okay, so there are other type of consequences we should be aware of. This could be another subject of study. Again, we cannot follow everything, but this would be wonderful. Anyway, now, with this same material, of course, I mean, it depends now if I am in a chemistry conference, bio conference, physics conference. Physicists would tell you immediately, hey, Clara, put some order in your messy natural material. And I agree with them. From a certain point of view, yes, to understand the fundamental aspects and the understanding of fundamental aspects drive any good technology, there is no doubt on this. But at the same time, I also have a part of the group just working with really materials extracted from natural sources. Anyway, if I want to put some order and understand the fundamental of my material and its physical-chemical properties, it's true that I have to go from the building blocks. So we work with excellent groups, excellent real chemist synthetic groups. They give us the monomers, and then we fabricate the film ourselves, so the polymerization happens in ambient condition, sometimes, I mean, catalyzed by the presence of ammonia. And so we kind of do the engineering of the thin films, and the thin films is really the core of our device. And so here we see the effect if we engineer the film, and for instance, we just start with the non-carboxylated monomer, where the order is more developed than when we have the carboxylated group adding space, if you want, to be during the self-assembly. So we have currents that are 3-4 times higher in this case than in this other case, as expected by an improved order, if you want, in the material. So sometimes we have to give some credit to physicists saying, hey, control since the very early stages, you will improve your performance. In this case, selecting so the non-carboxylated monomer gave us higher voltammetric current. This was true somehow. And now we are also at the point where we spin coat monomer, we have, I mean, for me, there is nothing better, essentially. Fascinating results really on the early stages of the growth in this material. The material grow under the atomic force microscope. So we just spin coat the monomer. And dendrimers form. There is a type of diffusion-limited growth that gave us wonderful dendrimers. But apart from the aesthetic pleasure, what we will try to do is really understanding how, after this structure, if we can control the structure, affect the functional properties, and finally, I mean, the performance of our devices. I don't know how many people here are interested in the, for instance, I cannot imagine, sorry, this is my ignorance, how if somebody is interested by skin cancer. But what surprised me, going even back, I mean, ordering the molecules, ordering the materials, controlling the early stages, it's also important because this is a Nature Communication paper of a few years ago from the Chemical Engineering Department at MIT. We don't know at this point, not even now, what are the chromophore in our material? So what is the responsible for the absorption of the UV light in our skin? So we don't know. There is a chemical disorder model, a physical disorder model. This MIT paper proposed that maybe a few tetramers and pentamers can help me to reproduce the spectrum of the natural melanin. So for people working in skin, people that deal with skin in the research and the absorption properties of the skin, I think it's plenty of room to study the chromophoric nature of the melanin pigment and its implications. Now, a last concept I would like to deliver. We go toward the end, and then I hope to receive your comments, your critics. Is the fact that, again, I mean, we are in an engineering school, and I think I'm very happy at the end of the day in an engineering school. So we show the redox properties of the melanin. We show the absorption spectra of the melanin. We came with the concept, let me go, we will come back later here. I jump a bit because I don't want to, can I, oh, it's a different presentation. Okay, no problem. I tell you something right now because I know what I'm talking about. I don't need too much more than this. But this is to say that we have in this moment a paper under review on a concept that might be maybe familiar to you, I don't know, but an organic solar battery. So we try to combine the light harvesting properties of the pigment, the storage properties of the pigment, so a solar battery that instead of integrating two different devices, for instance, a PV cell and then an electrochemical energy storage element, a supercap or a battery, integrate within the same material the two functions. And actually it seems to work. So we submitted, now let's see what the reviewer think about it. But it really works, so the charge that we can store in presence of simulated solar light is higher, both in terms of power density, energy density, with respect to what we can store in dark conditions. Now, before I conclude, I would like to tell you something. For you, it's normal to work in an aqueous medium. For physicists, it's a nightmare. The silicon microelectronics try to avoid at any cost the presence of water and salts. For you, this is everyday life. We measured the current versus time at different degree of relative humidity in the atmosphere of our melanin. And somehow we confirmed the hydration-dependent conductivity. We went further in this, collaborating with a really interesting group now at the University of California in Santa Cruz. So this group, this could be of interest for you. Maybe Noemi, you know it already. They reported a few years ago on a bioprotonic transistor, if you want. So H+, OH-, the analog of holes and electrons in conventional electronics, if you want. So with Marco, we evaluated protonic currents. This is current versus time, but now this current is a current of protons. And now we measure the current of protons. We measure with palladium electrodes that are activated once exposed to molecular hydrogen. They become palladium hydride, and so they become what is called protons. So if in your project you would like to evaluate protonic current, you can call this research group. They are expert in palladium hydride protons, and they can measure protonic current like my gold microfabricated electrode helped me to measure electronic currents. Okay, so we proved even in thin films with chemically controlled melanin the protonic transport in the material. Actually, we are in terms of mobility, we are on about 10⁻³ centimeters square volt second, comparable to what we have in water. And then another thing, and then I promise you that I'm done. Again, for you it's trivial. For physicists, it's a revolution. So you have water, you have salt. You want to study the fundamental properties of your natural material. So you make measurement, you pattern your substrate with metallic electrodes, typically interelectrode distance in the micrometric scale. You are in a wet environment because it's an hydration-sensitive material, so you really want to maximize the chance to detect properly your electrical response. And then what do you do, in your opinion? If you have a natural material, spin coated on a patterned substrate in a wet atmosphere, what is going to happen? Maybe that the physicist has to admit the existence of electrochemistry. And it has been really new. Huh? So I remember, and it was just one year ago, John Rogers spending 30 minutes at an invited talk in Phoenix, MRS Spring meeting, to talk to people about corrosion at electrodes, or the fact that gold electrodes are not so inert at the end of the day. So you are in a wet environment, you have gold, you have natural materials that intrinsically contain salt because they are extracted from biological media. You have to admit the possibility that electrochemistry is there, so you don't do just pure physics. You cannot just study charge carrier transport using the same model you were using for the silicon physics. Okay, so the first thing, we dissolved completely our electrodes, of course. So the chloride formed complexes with our gold, chelation properties of our melanin. Chloride present because melanin has been extracted from, sea medium, from the black, it's the black ink of the cuttlefish at the end of the day, yeah? So we form really dendrimers bridging the two electrodes within minutes. So if we don't want, as a physicist or physical chemist, to have confusing or misleading or totally wrong interpretation of our experimental results on the charge carrier transport properties of biomaterials, better to think about the chemical composition in terms of salts beside the organic material before doing the experiments. Okay? So we observed actually a sudden jump of the current. We thought it was the conductive form of melanin. These are gold dendrimers bridging the two electrodes. So if we don't want to be totally wrong, better to have an open mind. Otherwise, we can really make big mistakes. At the end of the day, this was a front cover in Advanced Functional Materials, so it was for good, but it was very surprising. Okay, so for instance, when you spin coat melanin extracted from natural sources on patterned microfabricated substrate, and you are in a wet environment, electrochemical reactions dominate the response under electrical bias. This has been exploited. We are now working on resistive switching memory devices, taking advantage of this dissolution of the electrode, if the dissolution is controlled, of course. Okay, so I come to a conclusion, and then I also want to deliver another concept, if you allow me. First of all, independently on the specific case of melanin, I think the effort we are doing, I hope they will be somehow useful to establish really methodologies on how to study natural materials chemically disordered because of the different polymerization sites, complex from the chemical composition point of view because they are extracted from natural sources, physically disordered as a consequence of the chemical disorder and complex chemical composition. So we kind of hope to contribute to establish rigorous, but at the same time, fruitful methodologies to explore these devices for a greener, if you want, optoelectronics and energy storage device. What we specifically observe, is that we prove the proton conduction properties of melanin, the presence of electronic conduction, for instance, for the moment, more in the voltammetric experiment, I show you the melanin versus poly-DHI results. I also show you, the interest, and sorry, really, I will explain you what happened with my laptop this morning. So I would have, I had in mind to show you the organic solar battery experiments. I couldn't, but anyway, we combined the two functions, optical absorption and energy storage in the Kenon redox sites, and so we proposed this organic solar battery concept. We saw that controlling chemically the building blocks, and so somehow going more bio-inspired instead of extracting from natural source, can, at a certain point, improve the performance of the device. We are now at the point, starting from this controlled melanin and the currents that we measure, trying to demonstrate melanin-based transistors. This would be in vacuum, so the transport here would be in vacuum, no proton involved, or more biocompatible and with low impedance neural electrodes. Of course, this aspect of the model of charge carrier transport is of primary importance to me, so two PhD students are just working on these very, very fundamental aspects. And so this is the panorama for the moment. So the concept I would like to deliver at the end, and this is more in terms of perspective, if you allow me. I think it's important to share with you, is the fact that in organic electronics, usually people wanted to impose somehow a certain order in terms of pi-pi stacking to promote a good charge carrier transport, so good, for instance, transistor performance. We are at the point, I think, where now the problem is no more the problem of the self-assembly. I would say that now the problem is the molecular disassembly. Guidelines for the molecular disassembly, so how to promote, how to predict and then promote the biodegradability, the destabilization of my device. So I see if up to now we have in the past we spent 30 years to stabilize, to optimize the molecular orbital overlap, I think we are at the point where now we have also to open our mind and say how we can destabilize in the fact that at the end of life, these organic electronic devices can be efficiently composted. For the moment, the results we collected with our melanin are not so good. Let's imagine if I can compost in a certain condition 70% of my cellulose, that is my reference, I can compost, just 10% of my melanin. And this we think is just due to the self-assembly properties of the material that make itself inaccessible to microorganisms for the compostability. So I think that there are concepts to understand, and we have to know what are the stimulus for us to open the supramolecular structure to make them more compostable somehow. This is one of the core problems in what is now ongoing, this green electronics network. So during the summer, NCERCA awarded to 15 researchers throughout Canada this NCERC Strategic Green Electronics Network, where the biodegradability, compostability of organic electronic devices is one of the key aspects beside the printability, as I was saying at the beginning, to limit the embodied energy in the device. So I leave you with these two concepts. If you have questions, they're more than welcome. Thank you very much.
I'm not sure if I understood correctly, but as far as I understood, melanin is a perfect conductive polymer. But when you said that you could microfabricate it, because I think we are pretty good at, from my point of view, I have lots of solutions for someone who needs a polymer to work in the body. But the main challenge that we have for an implant is just having a paternable, microfabricated, conductive path on it. So for me, what I care a lot is, even if it's not perfect as silicone or gold, if it can be patterned, I know, on a 10 micron pattern, that would be fantastic for me. Because I didn't get how you pattern it, actually. So can you just...
Okay. Leave me 1 second, so I try to be simple in my answer. If you have a redox active material, this doesn't mean that you have a metal, okay? Redox active, you have an electron transfer. To have a metallic behavior like, you have in gold, you really have to have a continuous transport of your charge carriers. So by definition, they localize throughout all the atoms of your metal. I might have said something that I didn't want to say. I didn't meant to say. It's not a perfect conductor. It's a redox active material, most probably a semiconductor, but we still use in electrochemistry carbon paper current collector, and when we do our fundamental studies, gold, platinum, palladium, iron, nickel, copper, these are all metals that we investigated up to now. But we need anyway our metals, let's say, kind of conventional metals. Now, I have to tell you something more. There are not too many, P.PSS is one of them, of course, not too many conductive polymer biocompatible, even less biosourced, okay? The patterning of the conducting polymer is feasible, of course. We are really working on this, so it would be a long story. I just invite you to come. We can spend a few hours, me, my first colleague, and we discuss about our patterning polymer, biocompatible polymers.
Okay, any other questions?
At one point you talked about the broadband nature, and I thought you were saying that was a good thing. But then you started talking about trying to control the creation of this thing, which I guess makes it less broadband. Is that correct?
It is totally correct, even if I didn't show it. So I think this is melanin in the sense really this reticulated material. I don't even want to call it polymer because it's not an ordered. I was in the lab of Dimitri Perepichka. One thing is to have regular polythiophene. One thing is to have natural, what I prefer to call macromolecules. Okay, it's different. It's not ordered. Building blocks are 2. Polymerization site are 3. One of the 2 building blocks has this carboxylated group with the protons that move whenever they can. So, disordered. And this is the featureless. We go to chemically controlled. This is the theoretical paper. The paper of Marcus Bühler is a theoretical paper here. Let me see. Where I had this Nature Communication? Yes, here. Of course, we go peaks, but this is what we see in our lab too. I'm just very slow in publishing. This is one of my defects. I'm very slow, but I can tell you that since at least 1-2 months, so the students were actually able to spin coat the monomer on a fused silica substrate, run to the building where we have an integrating sphere that decently evaluate absorption, reflection, everything, and we start to reveal peaks. And also infrared shift with the advancement of the polymerization, as it should be, because we kind of close this band gap with the increase of the delocalization of our electrons. So yeah, we go, I think this is really the result of having a physical and chemical disordered material. But if we can engineer the material, even just to understand, I think we go. This is what we are observing ourselves. This is what the theoretical papers show.
And are there some applications where that broadband nature is actually useful and you want to keep it?
We use the simulator solar light for our organic solar batteries. So it's not too bad, this absence of peaks, as long as what we absorb is a good amount of the incident photons, as long as, I mean, I have 1,000 photons and a good amount of these can be harvested and converted into stored electrons, I'm fine with this. A bit different could be if I want selective absorptions. Then maybe I have to go oligomers, very short oligomers, and control the polymerization. These are reactive monomers. I think if it took 40 years to people to understand the optical properties, it's because monomers are reactive. In nature, melanin is a very stable macromolecule. And actually what it's a part of, let me say, a bit of alchemic side of the story, this legendary melanin, is because it's really poorly soluble in all the organic solvents. In water, you have to go very basic environment, and ammonia basic environment. So a lot of story, I mean, somehow also, yeah, legends around the materials. And I think so the processability has been the issue. If now we're able to control since the early stages, maybe we can really understand if it's just a legend or if there is something serious to take.
Other questions?
I guess the question about when you're talking about, sorry?
At an orchestra, I'm the director of the orchestra.
All right. In terms of the way you can decompose these things naturally,
Yeah.
You're essentially generating unnatural materials and relying on naturally existing bacteria
Yes.
to decompose them. Does this sort of raise the question of perhaps we should be designing bacteria to decompose the new materials that you build? I know there's been some work on sort of doing selective breeding of bacteria to help eat particular plastics. And I'm wondering whether this is sort of an avenue of research.
Not me, I have to tell you that I'm totally ignorant. You give me an idea that I will transfer to my beloved microbiologist. Wow. Okay, I just submitted yesterday, I was where yesterday? I don't remember. I was in an airport and I just submitted a little thing to have a workshop. Okay, this is more material informatics maybe. But anyway, I think we need guidelines to predict and promote the biodegradability. I always thought that we should have, I thought in terms of molecular sciences, so how I have to arrange my molecules or disarrange my molecule. I don't know if the word disarrange exists. In Italian it should exist, let's say. And, but I didn't think about this other side of the story. So making the bacteria more ready somehow. So
Yeah, I mean, my understanding is they don't actually design bacteria. What they do is a forced evolution, where basically, you know, you do this business where you put a whole series of bacteria in, find the ones that that act, and then sort of purify them out.
So you want to educate your bacteria to compost?
Or find the ones.
Find the ones that do that.
Either find the ones or
Okay.
force.
Yeah. I understand the concept. Sorry, it's very new to me. Of course, I will take it and I will think about it. Yeah, very good. Didn't know.
So
Wow.
I have a question about the stability of material properties. For example, the battery application.
Yes.
How many charge cycles do we see until like the battery efficiency starts to drop?
20,000, 25,000 about? Yeah, it's decent. It's surprisingly decent. And look, I'm very conservative and slow when it comes to publishing. I mean, excessive, ridiculously slow. Students are not always happy, I have to be honest, but we run really more than 20. And what is surprising, it's stable even under light conditions. I mean, the field, my experience is that the field of organic photovoltaics has been killed essentially by the limited stability of the organic semiconductors, P-type or N-type, limited stability. We see that, I mean, it just survives to 1,000 cycles. Here, because for the Super Cup, we did more than 20,000. Here, I think we did 5,000, 6,000, but it seems to work. Now, it's just in the lab, it's an exploratory study, of course, it's just an article. But these few thousand cycles are pretty decent, yeah. And if you allow me, yeah, we can compare the organic solar cells or the organic solar battery, but not too much. I mean, the two environments are completely different. In one case, we are solid state. In the other case, we are immersed in an aqueous environment in presence of salts with a certain ionic strength. So I don't want to push too far the comparison, but we were surprising about the stability in light conditions.
Other questions? If not, I have just a very quick question. Oh, there's another question? Oh, okay. Students.
Just with regards to the stability of the material that you're manipulating, just exactly how much time does it take to be degraded biologically? Have you done any tests with regards to that?
Okay, so let me be funny 30 seconds. So I was cleaning my laptop this morning. I put too much spray on the clavier. It's not accessible anymore. I cannot digit even the password, because otherwise I would show you all the results, okay? I'm very sorry. So Dropbox just allow me now in 2 minutes to extract the presentation that luckily I did on time. The compostability, it's not even us that we decide. We are following international standards. So it's a few months, 90 days. You can even after extrapolate, but this is ASTM protocol. So the temperature, the number of days, the type of microorganism, we have to follow rules to be consistent with other type of materials we want to compare. Because we go in parallel, we do polyethylene, by definition not degradable, cellulose, and our organic electronics material. We tried 3. Melanin was the only one biosourced, other 2 synthetic, one coptephtalocyanine actually, and another PCS polymer. But this is, I can send you all the information because this is the ASTM 3880 standard. We didn't invent anything because it's already extravagant enough, the material, so we try to control other parameters.
Okay, sounds great. So let's thank Professor Santato.
Thank you very much to you.
We will be here for another few minutes if you have additional questions.
Yeah, absolutely.